So today we are going to discuss about heat transfer and energy conservation in glass. Okay. So why this? I have taken this topic because heat transfer in glass is something different, and we need to understand that. We consider this for load calculation as well as for energy simulation. Okay. So that is why we have discussed about heat transfer through wall. Okay. But heat transfer through glass, so it is something different and significant. Okay, so that we have to have a special session for that. So that's why I'm taking it today. Okay, so we will go to the subject. Um, so heat transfer through glass, I think it is associated with the radiative heat transfer, conductive heat transfer, and convective heat transfer. So all the three types of heat transfers will be involved in the heat transfer through glass. Okay. So for that, first we will know about the radiations. So already we know that the radiation from the sun, it will be basically in two components. One is the direct component and the other one will be the diffuse component. So the direct component of the radiation, it is a short wavelength and high temperature. Okay. So it is a direct component is short wavelength and high temperature. The diffuse component is long wavelength and comparatively low temperature. Okay. So direct radiations are coherent, or it will be straight line. Okay, it is in the form of straight line, so it is highly directional. Okay, the diffuse radiation, so it is not highly directional because the name itself it tells that this direct radiation, when it is falling on multiple surfaces, it will undergo multiple reflection. Okay, for example, when the earth the solar radiation is entering the earth, it will maybe falling on the cloud, trees, ocean bodies and other surfaces which are available on the surface of the earth. So because of that, it will undergo multiple reflection. Okay, so because of multiple reflection, so the direct radiation will be diffused. So outside the earth atmosphere, everything will be in direct radiation form only. When it enters the earth's atmosphere, so it will be split into direct radiation and diffuse radiation. So that is how we are having a direct radiation is having more energy, okay, with the short wavelength, and diffuse radiation it is having less energy with the longer wavelength. Okay, so this also we should understand when there is multiple reflection of the direct radiation. So my direct radiation will be converted into diffuse radiation. So that is what will be happening in a house also. If the if the direct radiation is entering into the house during through the glass, so it will undergo multiple reflection inside the room. Okay, so whatever the object it is there, so it will undergo multiple reflection. So because of that, okay, the short wavelength will be converted into long wavelength, or in other words, the high energy state it will be converted into low energy state. Okay, low thermal energy state. Okay. Okay, so not only this, the direct radiation it may fall on the surrounding surfaces also. For example, if you are having a building side by where you are, that building is plastered with heat reflecting films. Okay, so that means the reflected rays from that building also it will be falling on our building. Okay, so that also we have to take it. Okay, so not only that, if you have water body and other reflective structures nearby the building, so then we will have reflective radiation also. So mainly two types of radiations very important: direct radiation. Okay, and the next one is the diffuse radiation. Okay, what will be the response of the glass, okay, for this radiation? Okay, so if I am taking a 3 regular sheet, okay, regular sheet of glass, so you will find that the transmissivity is more for a longer wavelength spectrum. Okay, transmissivity is more for a longer wavelength spectrum. Okay, so suppose if I am taking 6 thick gray heat absorbing glass, so what happens? The transmissivity is reduced. Okay, so the transmissivity is transmissivity is reduced, and you can watch that the transmissivity is dependent on the wavelength. Okay, it is dependent on the wavelength. Okay, and when I'm going for 6 green heat absorbing plate, okay, it is green tinted heat absorbing plate. Okay, so I'm finding that the transmissivity is reduced. Okay, transmissivity is higher on the lower wavelength range, and at higher wavelength the transmissivity is reduced. Okay, so that means the transmissivity I have to find out by integrating this, okay, through the wavelength, and then only I can find out what will be the transmissivity. Okay, so and that is what the heat transfer through the glass. Okay, so it is special. Okay, so we need to know about that. So first of all, whenever the radiation is falling on any surface, okay, so first, if you consider the surface to be transparent, okay, or semi-transparent, okay, so what will happen is a portion of the radiation will be transmitted, okay, because it is transparent. A portion of the radiation will be transmitted, a portion of the radiation will be absorbed, a portion of radiation will be reflected, okay. For example, you consider that the total radiation, it is equally divided. So that means one third is transmitted, one third is absorbed, one third is reflected. In other words, I can say, if I consider that radiation incident on the surface to be 100%, 33.33% is transmitted, 33.33% is absorbed, and 33.33% is reflected, okay. So that is what I'm finding it here, okay. So from this I can refer to the property of the material. So if I am having a fully transparent material like white glass, so the transmissivity, the portion transmitted will be very much higher, okay, and the reflected and the absorbed will be smaller, okay. Similarly, if I'm having a opaque surface, what will happen? The amount transmitted will become smaller, okay. The amount absorbed and reflected, it will become higher, okay. So that is how the properties of material will be affecting the percentage of radiation which is transmitted, absorbed, and reflected, okay. So that means if there is a glass material, okay, so depending on the property of the glass material, so you will have the amount of radiation, okay, which will be transmitted, absorbed, and reflected. Now I told, for our case under consideration, I told 33.33% is transmitted, 33.33% is absorbed, and 33.33% reflected. So that means I have 0.333, okay. So that is the transmissivity, and 0.333 is the absorptivity, and 0.333 will be reflectivity, okay. So if I'm telling in percentage, it will be 33.33. If I'm telling it as a coefficient, okay, so then it will become 0.333, okay. So that is how the properties are mentioned, okay. So similar to that, we will be having various properties of the glass materials. So if I am saying the transmissivity of a particular glass, if it is more, so it means that it is like a white glass, okay. So from the white glass, you know that the amount of radiation it is transmitted through the white glass, it will be higher. So that means the transmissivity of the white glass, it will be higher, maybe around 70%, okay. So then I can tell the transmissivity is 0.77, okay. Similarly, if it is a heat reflecting glass, so think that I'm pasting a film, okay, in the surface of the glass, okay. So what happens? The heat will be reflected, okay. Most of the heat will be reflected, less will be transmitted, okay. So that means the transmissivity of the glass will be around 0.1, okay. So and the absorptivity and the reflectivity will be higher in that case, okay. Absorptivity will be 0.33 and the balance will be the reflectivity. So what is the meaning of this discussion? It says that the sum of absorptivity, reflectivity, and transmissivity will be equal to 1. And, what is this equation? It is the equation for energy balance in a radiation which is passing through a semi-transparent material, okay. So what is the meaning? What is the meaning of absorptivity? It is absorbed radiation by incident radiation, okay. Reflectivity is reflected radiation by incident radiation. Similarly, transmissivity, transmitted radiation by incident radiation, okay. So I told all the three are 33.33% means this will be 33.33%, this will be 33.33%, this will be 33.33%. If I add everything, it will become 100 or 99.99%, so it will be 100%, okay. So in other words, I can say this is 0.333, 0.333, and 0.33. Totally, it will be 100. Always it will be 100, okay. So the if I take the total incident radiation, it will be if it will be some value, okay. It will be split into split into this radiation incident will be split into transmitted, absorbed, and reflected. So based on that, I will be having the factor, okay. For example, if for a heat reflecting glass, okay, so the transmittivity will be 0.11, okay. So absorptivity and reflectivity will be 0.5, and the balance will be absorptivity. So that is how I'll be having. For a fully opaque wall, okay, for example, if you take a wall like our building wall, so there transmissivity will become 0. There will be only absorptivity and reflectivity. The value of absorptivity will be more and reflectivity will be smaller depending on the color. So that is how, okay, so even for opaque substance also I can do the radiation energy balance, okay. So this equation is very important, okay, this equation is very important that you should understand, okay. So for a white glass which will be allowing more radiation into the building, so the transmissivity value will be higher, okay, and the glasses which are not allowing the radiation into the building, so the transmissivity value will be less, okay. So when the transmissivity becomes less, automatically absorptivity and reflectivity will be increased, so that you can understand. So what happens if absorptivity is more? If absorptivity is more, it will, you know that the solar radiation will be absorbed in the glass structure. So because of that, the temperature of the glass structure will be increasing, okay. The temperature of the glass structure will be increasing. So that is also important, because in that place at that point, if absorptivity is more, then temperature of the glass will be more, then conduction convection heat transfer will be taking place on the surface. So what is the meaning? If the transmissivity is more, okay, so the radiation will be the light and radiation will be entering in the form of radiation itself into the building. But if I reduce the transmissivity of the glass, okay, what will happen? The radiation will be absorbed in the uh, glass material. Okay, so then conduction will be taking place. Okay, so this is very, very important. So we have to understand this. Okay, mostly we don't. We may not be thinking about this. Okay, but this is very important concept. We have to understand. Okay. Okay. So now. So this is the solar radiation which is falling on the surface of the earth. So regarding this, we had a detailed discussion already. So I told that any place we can every day we can find out what will be the solar radiation falling on the surface. So this is for 40° north latitude. So if it is so this is given in the data book. Okay, so even in energy simulation they are using this data, and it is given for various months. Okay, and it depends on the radiation only. So this depends on the incident solar radiation watt per meter square. Okay, and for 40° north latitude, you should be knowing the amount of radiation which will be falling. Okay, so that will be lesser. 40° north latitude means it will be lesser in the December solstice, and it will be more during the June solstice. Okay, so in the December you can see the horizontal radiation will be lesser. Okay, so if I am going for the July near June, which is near June, so horizontal radiation value will be very much higher. So this data is given in the data book. So when we are calculating the load, okay, so usually what we will be doing is we will be multiplying with the coefficient. Okay, so that is that shading coefficient and SHGC coefficient. I have to multiply the area SHGC with this number. Okay, so that from that I will be directly getting what will be the radiation at a particular point of time. Okay, so this value is in watt per meter square. Okay, so that means if I multiply by meter square, area in meter square, I will be getting in watts, and that will be for a pure white glass, which will be allowing all the radiation inside. But in reality, the glass will not allow all the radiation inside. So that means there will be some coefficient which will be limiting the radiation entering into the building. So that coefficient, it is HS, solar heat gain coefficient. Okay. So that means we will define what is the solar heat gain coefficient. Okay, so solar heat gain coefficient. Okay, much before going to solar heat gain coefficient, so let us revisit the energy balance in a glass again. Okay, so here one such, I am taking a distribution of solar radiation in the glass. So I am taking one such glass. Okay, one such glass. So where the solar radiation is incident on the surface. Okay, so if I'm having 100% solar radiation, okay, so what is happening is 80%. Okay, so it is almost like a white glass. Okay, clear glass, 6 mm clear glass. So 80% is transmitted inside. Okay, it is transmitted inside. Okay, and 80% is transmitted inside, and 8% is reflected, and 12% is absorbed inside in the glass. This 12% which is absorbed in the glass, it is responsible for raising the temperature of the glass. Okay, and if you are having more transmissivity, the temperature rise in the glass will be smaller. Why? Because 80% of energy is entering inside because it is a white clear glass. 80% of the energy is entering inside. So that means the absorbed component will be smaller. Think about a case where the transmissivity is less. For example, if 30% is transmissivity is there, okay. So what will happen? Balance will be reflected and absorbed. So then the absorbed portion will be very much higher. So that means a glass with a lesser transmissivity, it will have more absorptivity. That means more rise in temperature in the glass. So that we have to understand. When the temperature of the glass rises, what happens? So inside you will be having conditioned space. Okay, so that is the air conditioned room will be there. Outside you will be having the ambient atmosphere. Okay, so mostly inside you will be having a lower temperature. Okay, compared to atmosphere. Okay, so mostly in air conditioned space you will be having around 24 degrees or 25 degrees inside the space, conditioned space. Okay, so the absorbed heat, it will raise the temperature of the glass. So the high temperature, okay, from because of this high temperature, this will try to transfer heat to inward as well as outward. Okay, so how it will transfer heat inward and outward? So it will the rise in temperature, the temperature will be higher in the glass. Okay, and after that, okay, so it will be just seeing where the resistance is low. Okay, whether it is inside or outside. Okay, two things it will see. First, it will see the temperature difference. So if the temperature is low here, okay, and it will try to move this side. If the temperature is low on this side, okay, so it will move this side. Okay, first it will look for the temperature. Wherever low temperature is there, the flow will be there. Number one. And the next it will look for the heat. Suppose if both are having almost equal temperature, then heat transfer coefficient also it will be seen. Okay, so in that case, if it will see how much is the inside heat transfer coefficient and the outside heat transfer coefficient. Okay, so two factors are important: the temperature of the place and as well as the heat transfer coefficient. Okay, so that will decide the resistance between these two places. Okay, that will decide the resistance between these two places. So wherever the low resistance is there, the heat will try to flow. Okay, the heat will try to flow towards the place. It may flow towards the room or it may flow towards the ambient. It depends on the temperature. Okay, wherever the lower temperature is there, the flow will be there, and as well as it is dependent on the heat transfer coefficient also. So mostly inside we will be having lower temperature, outside we will be having higher temperature, and the heat transfer coefficient, it depends on the velocity of the airflow. Okay, so this is the concept. This concept we should understand. So that is how I have an inward transfer based on the condition. I have an inward transfer of around 4%. Okay, and outward transfer of around 8%. Okay, fine. So that means the total 100% radiation which is coming here, because it is 6 mm clear thick glass, 80% is transmitted, 8% is reflected, and 12% is absorbed. In that, out of this 12%, 4% is entering into the room, and 8% is entering, leaving the wall. That is going to the ambient, outside atmosphere. Okay, so this is very important. We have to understand this. Okay. And one more thing also, one more point also I told, if it is for a clear glass, okay, the amount of heat absorbed by the glass, absorptibility will be less, so heat absorbed by the glass will be very much lesser. But if the amount of heat transmitted into the building, if it is less, so then absorptibility will be more, so that means the temperature rise in the glass will be very much higher. So this point we should note it. Okay. Okay, now after knowing that, we can go to the definition of what is SHGC. Okay, so SHGC is the solar heat gain coefficient. Okay, so from the discussion whatever we had, okay, the solar heat gain through the window divided by the solar radiation incident on the window, it is SHGC. Okay, so what does that mean? So the solar heat gain inside the building divided by total incident radiation. Okay. So that meaning is this is total incident radiation. So what are the radiation which are entering into the room? So the part which is transmitted and the part which is because of heat transfer entering into the room. Okay, so that is because of absorptivity and the heat transfer into the room. So two parts are there. So that is what we are finding here. So transmissivity, it represents the fraction of radiation transmitted, and absorptivity, it represents the total 12%, in that the fraction fi that means 4%. Okay, so or whatever the percentage of this 12%, that is fi into alpha s. So if I consider this as the total, this is the percentage of heat entering into the room, okay, into absorptivity. So now it's very simple. If any glass material is there, just you'll be this is a property, okay. So tau s is the property of the glass, okay. Transmissivity is the property of the glass. Similarly, alpha s is the absorptivity, that is also a property of the glass, okay. Fi is dependent on the external conditions, so it depends on the temperature, or it depends on the convection coefficient, okay, inside or outside. So now what is SHGC? It is a percentage, very simple. The percentage of heat entering into the building divided by total incident radiation, okay. Percentage of heat entering into the building. So what is the percentage of heat entering into the building? It's very simple. Amount transmitted plus absorbed. In that absorbed, what is the fraction entering into the room? That is it, okay. So now if this coefficient is given, so if you want, when you are going for a cooling load calculation, or if you are going for energy simulation calculation, so what you can do is you can take this SHGC coefficient, okay. So this is the solar radiation, Q dot solar radiation, so that we have seen in our this is the fraction, okay. So this is the radiation incident at any particular point of time. So that value in watt per meter square, you can put it here and multiply by the meter square area of the glazing. So I'll be having watts. So this will be watts. This have no unit. This is a fraction. So when I multiply, I'll be getting the solar heat gain through glass in watts. Okay. So that is the significance of SHGC, solar heat gain coefficient. Okay. Sometimes we will be interested in comparing the solar transmission property of the glass. Okay, so we'll be interested in comparing the solar transmissivity property of the glass or SHGC property of the glass. Okay, so what we are doing is we are taking the SHGC of the product under consideration. For example, some product is given to you. Okay, so you take the SHGC of that glass. Okay, you compare it with the SHGC of the reference material. Okay, the mostly used standard reference material, it is 3 mm thick double strength clear window glass sheet. Okay, for which the SHGC value is 0.87. Okay, SHGC value is 0.87. So now what when I want to find the shading coefficient, okay, shading coefficient. So it is SHGC of the glass under consideration, or whatever you are using for the building, divided by the SHGC of the reference material. I told you already about that 3 mm thick double strength clear window glass. Okay. Okay. So now I have SHGC divided by 0.87. Okay. So it is 1.15 into SHGC. Okay. 1.15 into SHGC. So now this. Okay. So this will tell you how much. Okay. So how much is that? How much is the radiations will be entering into the building, okay, compared to a standard glass material. Okay, so it is like you have something called density, and the ratio of densities we call it a specific gravity, like that. So this is like density. I'm taking a ratio of that. It is I call it as the shading coefficient. Okay, we are comparing two substances, that property of two materials. So one is our material and the other one is the reference material. Okay, so that is how I have the shading coefficient. Okay, so shading coefficient is also an important property of the glass. Okay. Okay, so the next, when we are going for the heat transfer through glass, so this slide is very, very important. Okay, so when I am going for heat transfer through glass, so first whenever the radiation is entering, so I told that it will be entering in two forms. Okay, so one is in the direct form and the other one will be the diffuse form. So how that I can understand whether it is a direct radiation or a diffuse radiation. Okay, so it's very simple. Whenever you are in the room, so you will find that the solar radiation directly, solar light directly, it will be entering into the room through the glass. Okay, through the white glass. So you can actually, you will be seeing that sunshine which will be entering into the room. So that is the direct radiation. Okay, so that is the direct radiation, whatever we are saying. Okay, so this direct radiation, it will be there only if there's only if the solar radiation or the solar visible radiation which is entering into your building directly. Okay, so if it is entering directly into your room, so you can even see the light which is entering into the room through the window. Okay, so that is the uh, uh, direct radiation component. Okay, and it is also possible, okay, it is also possible, this light, it will be there in your room. Okay, when the sun moves, after that this light will disappear. Okay, but can we think that after this light has disappeared, can we think that the radiation is not entering into the room? No, you know that light will be entering into that room through that. Okay, so that means now light is entering, but now it is not very intense like you seen previously. Okay, but now it is diffused, but the diffuse component still it will be entering into your room, so that is called a diffuse component. Okay, so when so what is the amount of heat entering into the building? Okay, so previously I told the transmitted portion plus the whatever the fraction entering into the room. Okay, so this is the fraction entering into the room through convection from the glass surface. So this is Tg, means it is the glass surface temperature, and Ti is the inside room temperature, A is the area of the glass, Fi is the Ha, that is inside heat transfer coefficient. Okay, so this is the amount of heat converted into the building. Okay, uh, uh, from the surface from the glass surface because of the high temperature Tg. Okay, so this is convective corrosion. Okay, but the amount of radiation transmitted, and it is split into two. One is that direct radiation. Okay, so accordingly I have a transmissivity for direct radiation. Okay, so what is the meaning? I told you can sometimes you see the sunlight will be directly entering into the room, the rays of the sunlight, you yourself can see that. So that is what I told, it is the radiation. So you have a separated transmissivity for the direct radiation. Okay, and this rays which is entering into the sun, the rays of the sun which is entering into the room, it need not fall for the full area of the window, it need not fall on the full area of the window. For example, so you can take this example. Okay, when sun is here, okay, when sun is here, you can see it is penetrating, it will penetrate like this and it will be entering inside. So here inside you can see that the sun's rays will be there. So that means that is direct radiation, that is direct radiation which is entering. So inside you can see the visible light which is falling, light of the sun which will be falling. Okay, so now that area is this area, full area. Okay, now you think that the sun has moved from this position to this position. When sun is somewhere here. Okay, so what will happen from here to here? So the sun will, because of this overhang, sun will not be falling on the full glass. Okay, sun will be falling only in half of the glass. Okay, sun will be falling on the half of the glass. That means when sun is here, it will be falling fully. Okay, similarly sun is here, it will be falling, okay, fully. But when the sun comes in this position, okay, this position, from here the direct rays from sun, it will come and fall only into the lower half only, top half you will not be available. So that is what I say is the radiation A sun. So A sun is different from that of the window area, so that we have to understand. Okay, A sun means the A sun is the portion of the window which is available for the direct radiation from the sun. Okay, so that is called A sun. So this is the transmissivity for the direct radiation. This is direct radiation. Okay, then what is the diffuse radiation? Diffuse radiation, again we can go here. Diffuse radiation will be there here when the sun was there directly, but now the sun has crossed here. Okay, sun has crossed this position. That means you will not see that sunlight falling into the room. Okay, but still here you can see the light, you can see the light here, and because of the light will be entering into the room, and again visible light radiations will be entering. But this light, okay, so this light will be in the infrared spectrum, okay, at low energies. But that also we have to account. But that light will be falling on the full area. That is very important. That light will be falling on the full area. So that is what I say. When it is diffuse radiation, I take the full area of the window. Okay, and the corresponding transmissivity, that will be different. This transmissivity will be different, and diffuse transmissivity will be different. Okay, and then I have to take the diffuse radiation also. Okay, so this is the exact amount of radiation entering into the room that we have to understand. Okay, this is because of the direct sunlight. Okay, direct sunlight, and this area of the sun will be varying. Area of the sun will be varying. Okay, and this is because of the uh, diffuse sunlight. Okay, diffuse sunlight, but it is always available because light is always available. This is always available for full area of the window. And after that, because of the temperature rise, okay, in that glass, so I have HA TG minus TA. So this we have seen here also. Okay, this portion only I'm telling. This portion only because of temperature rise, it is HEA into temperature TG, temperature of glass minus it inside the room temperature. Okay. Okay. So now this is fine. So the next is we have to find. Okay, so we have to find what will be the uh, energy balance. Okay, so here you can see the next is, okay, so the next is what happens to the absorbed radiation. What happens to the absorbed radiation? So the absorbed radiation, it will rise the temperature. We have discussed in the last slide. So there also, in the absorbed radiation also, you know, the absorptivity will be more when the sun is directly falling, direct radiation is falling on the glass, and the area of the contact also, it will be more. Okay, or sorry, it will be varying. Okay, when for the direct radiation, same discussion applicable here also. So at this point, whenever you are having this transmitted radiation, at the same point, absorption also will be there. So that means the area also I have to take the corresponding area only. Okay. Similarly, the diffuse radiation. Okay. At the point of diffuse radiation also, the absorptivity will be there. Okay. And that components I have to put it here. So here it is absorbed. AD means it is absorptivity for direct radiation. A small d is the absorptivity for the diffuse radiation. When I add this absorbed radiation component, okay, so that will be equal to the heat convected into the room. So again, it is the same thing only. This is the absorbed component. This 12% is the absorbed component. It has direct component as diffuse component, okay, and that will be equal to HA del T on this side as well as HA del T on this side. So that is what is given in this energy balance, okay. So this is the total absorbed component, and I have the total area into HA del T on the inner side and HA del T on the outer side. A I am taking outside. So this is just an energy balance equation. Okay, so that means what is the heat which is transferred into the building? So I have one component is because of the transmissivity of the glass, where I have a direct component, direct radiation transmissivity component and the diffuse radiation transmissivity component. Okay, then I have and apart from this, you will be having a steady state heat transfer. That is because of the temperature difference between inside and outside. Okay, because of inside convection, outside convection, and as well as the thermal resistance of the glass. Okay, so that is how you will have U. Okay, 1 by HA, 1 by HO plus L by K of the glass plus 1 by HO. So that is total resistance. I take reciprocal of that, I will be getting the overall heat transfer coefficient. Okay, so U into A into TO minus TI, it will be the steady state heat transfer. So that also will be existing because of the temperature difference. Okay, and the portion. Okay, so I am taking the diffuse portion, and the portion which is entering into the room, I am putting it by this fraction 1 plus FO by Fi. That is, HO is the outside heat transfer coefficient, Fi is the inside heat transfer coefficient. So that is what I tell as the total heat entering into the building. Okay, so this heat transfer process, it's very interesting to know. Okay, unlike other type of heat transfer, so it is different and very interesting to know. Okay, okay, fine. So and we can find, okay, so there are different types of glasses. So the properties also will be varying. If it is a clear glass, I have a shading coefficient as 1. That means all the radiation will be entering into the building compared to 3 mm glass. 1 means what? 3 mm glass only, you will get 1, because for that only it is 0.86 and 0.86 by 0.86 will give me 1. That means it will it is having maximum transmissivity. It will allow all the radiation. So that means 86% of radiation it will be entering inside. It is not. It will not allowing 100%. Okay, it's not allowing 100%. It is allowing 86%. Okay, but when you are comparing with the 0.86, so it becomes 1. Okay, so now when I increase the thickness, okay, I'm finding that the shading coefficient is decreasing. So that means the amount of energy entering into the building is decreasing. Okay. Similarly, if I'm having heat absorbing glass, like a tinted glass, okay, so again this value is decreasing. Okay, and if you are going for a double glazing, okay, so again you will find that your shading coefficients will be decreasing. Regarding this, we will have a discussion. Okay, and if you can use the drapes or internal curtains. Okay, so that also it can help you, okay, in reflecting the radiation. If you are using a reflective cloth for the drape, okay, that is very important. If you are using a black cloth, it will absorb the radiation inside. Okay, if you are using a reflective cloth, and it will absorb and that it has to reflect back. Okay, but sometimes, okay, so it will absorb and it will release the heat inside the room itself. Okay, so that is also possible if you are having a dark colored drapes inside the room. Okay, so it will absorb and the heat and it will be releasing slowly into the room. So that is also possible. Okay. Okay, so now SHGC is the percentage. Okay, so 0 SHGC means no heat is entering into the. And if it is 1 SHGC means it is 100% heat is entering. 50.5 SHGC means 50% of heat is entering into the building. Okay, and we have visual transmittance. Okay, so we have higher visual transmittance and lower visual transmittance. Okay, so what is visual transmittance? So in the visual transmittance, it is about the visual visible light. Okay, so somewhere because especially at the beyond the 30 degree north latitude and all, the day's length problem will be there. Already we have seen discussed about the day's length. So if the day's length will be less for most of the time, and most of the time it will be dark when you are going towards the poles. Okay, so most of the time it will be dark. So at that point of time, you will be interested in taking the visible light from outside. Okay, so for that you may use glass with higher visual transmittance. Okay, and similarly when you are in the equator region, so you want to reduce the heat entry into the building through the glass. For that you will reduce, already light will be higher, so you can use the glasses with a higher lower visual transmittance. So it will be like a tinted glass, green glass, like this you can use it. Okay, so this will reduce the visual transmittance. Visual transmittance is also an important property while selecting the glass material. Okay, so when you're going for a commercial glass, okay, so for a commercial glass, if you refer to the properties, they will be giving the properties like this. Okay. So here you can see this is transmittance. So what is the percentage ultraviolet prevention? So that is given here. Okay, so for various types of glasses it is given, and what is the percentage of visible light it will be allowing? So that is given here. Okay, so and these are all various varieties of the glass. Okay, so various varieties of the glass, and how much percentage total solar energy it will be reduction with that. So that is also given here. Similarly, the reflectance property is also given. Okay, and most important thing is the U value is also given. Okay, you can see U value is also given. So some of you, okay, so you may be wondering why U value is given for a glass. Okay, so U value it is important. Why? Because we have seen about two types of air conditioning. One is the summer air conditioning, other one is the winter air conditioning. For summer air conditioning, load calculation, everything we do it transiently, because you know because of solar positions. Okay, so a lot of transients will be there in the load calculation. But when you are going for the winter air conditioning, so you know we are designing the system based on the peak winter, that is nighttime condition. So during the nighttime conditions, already I told you the radiations will not be there. Radiations, this radiation, transmissivity, these concepts will not be there. For example, you think you are having a glass, okay, in a winter country, for example, in Scandinavian countries, okay, very cold place. So nighttime when it is working, there will be just heat transfer only. Okay, so outside the temperature may be minus 15 degrees centigrade. Inside the temperature will be around 15 degrees centigrade because you will be using a heater. So at this point of time, from inside to the outside, transmissivity and other properties will not have a say. Okay, during night time. Okay, so only this will be having a say. That is, heat transfer will be having a say because there is no light. Outside it is winter, so inside you will be switching off your light and you will be sleeping. So at that point of time, from inside to outside, there will not be any radiation heat transfer, or from outside to inside, there will not be any radiation heat transfer. So at that point of time, this is very, very important. Your overall heat transfer coefficient becomes important. You have to decrease the overall heat transfer coefficient, like how you are decreasing the overall heat transfer coefficient for wall. Okay, you have to reduce the overall heat transfer coefficient for a glass. So that means you require an insulating glass. So insulating glass means a glass with low U value. Okay, but already glass itself is an insulator. We use glass fibers as the insulators. Okay, and that means you require a glass with low U value for handling the winter in the handling the building. Okay, in the winter conditions. Okay, so that is how this U value becomes important. So this we should understand. So U value becomes important in Western countries or cold countries, very cold countries, especially during night time. Okay, so that we have to understand. So then they are giving the shading coefficient. Just now we have seen what is the SC, shading coefficient. It is SHGC of the material under consideration divided by the SHGC of the 3 mm double plan glass. Okay, so they have compared and they have given the value. Okay, and also we have studied about the solar heat gain coefficient. So that, which is the product of transmissivity, sum of transmissivity plus absorptivity multiplied by the percentage entering into the room. Okay, so you can find both these properties are decreasing when you are decreasing the transmissivity. Okay, so you are finding both these properties are decreasing. So that means the amount of heat entering into the building or light entering into the building is reducing. Okay, so that properties you can see. So when you go to the supplier, you will have properties like this. Okay, some they are giving light to solar heat gain. So that means if it is giving more light than solar heat gain, then this property will be more. Okay, so that means 1.85 means more light than the solar heat gain. So that is how we have to. So you have to see the properties. Okay, so you have to select the properties accordingly. When you are taking for summer conditions like in India, okay, so there you will always try to reduce the heat entering into the room. So in that case, you have to reduce the transmittance. Okay, so you have to reduce the transmittance and you have to go for lesser transmittance. Here in India, if you are going for a lesser U value, okay, so because we don't have a very cold winter and we may not be using okay, the air conditioner during the winter, or even if you are using the air conditioner in the winter, okay, a low value, low U value, it will not have a very high say like you have it in cold countries. In the cold countries, the outside temperature will be -15, the inside temperature is 15. So the overall temperature difference itself, it will go up to 30 degrees. Okay, 30 to 40 degrees also it will go. So that means there that U value is very important. For our place, transmissivity is very important. Okay, so these are the things which we should know. Okay, while selecting the glass. Okay, so okay, so we are talking about the glass selection. So we can find that the radiation heat transfer between the room and window is proportional to the emissivity of the glass. Okay, and emissivity is also very important. So like emissivity of the glass on the surface, emissivity or absorptivity of the glass is also an important parameter. So if you are having a low emissivity interior glass, it will reduce the heat loss by radiation in winter. Please underline this. Okay. Similarly, tinted glass and glass coated with reflective films reduce the solar heat gain in the summer. So during summer, it will reduce the heat transfer. Okay, because tinted glass means you might have seen the colored glass or inside tinted glass. Okay, the surfaces may not be smooth. Okay, so it will be tinted. So this tinted and glass coated with the reflective films. So this will be absorbing more amount of radiation. Okay, transmissivity will be less and it will be absorbing more amount of radiation. Okay, and it will be useful in the summer and as well as in winter. Okay, and similarly you can reduce the conductive heat gain, okay, or losses by minimizing the multiple pan windows. So you can use single pan, double pan windows, okay, for reducing the heat gain or heat loss. Okay, so we will consider cases. Okay, so first we will go for warmer climate like our place. So in a warmer climate like our place, what we can do is in the glass on the outer surface you can put a reflective film. This is very important. You have to put a reflective film on the outer surface. So what is that you are doing? Because you know in our place under radiation will be very much higher. Okay, so first you have to limit the radiation. So what is that you are doing? Outer surface you just put a reflective film. Okay, and after thing, this will be entering into the building. So then you will be having a low E film on this side of the window. So when I am putting your low E film, okay, so that will also reduce the heat and radiation from this side to this side, and similarly even the radiation from this side also it cannot come to this place. Okay, so that is the advantage. Okay, so that is the advantage what you have it. Okay, so that means if you are using a in a warm climate like Chennai or Bangalore or whatever in the South India, so you can have a reflective film, okay, on the surface, okay, and you can put a low E film on the inner surface, okay? And you know, because the glass temperature will be higher, you know, when you are putting a reflective film, we are reducing the transmissivity. When I am reducing the transmissivity, reflectivity and absorptivity will be increasing. Because of that, the surface temperature of the glass will be higher than the room. This also you have to note. Here you can see the surface temperature of the glass is higher than the room. So what will happen from here only the radiation will be transferring from this side. Okay, from this side to this side it is not possible. That is also advantages for us. Okay, that is also advantages for us. So this is what we should do in a warm climate. Okay. Similarly, when I am going for a cold climate, here also it is very interesting. Okay, in a cold climate, okay, like beyond 40° north latitude and all. So it is a part of procedure that you have to harvest the solar energy through the glass into the building, because throughout okay night time and all it will be very cold. Okay, so during the daytime, okay, so you want to heat the building. So when you want to heat the building, you can use you can use electric heaters or heat pumps, or otherwise what you can do is you can tap the solar energy through the glass. So how you can tap the solar energy in a cold climate? So I take the cold climate, so I have to tap the solar energy. So what I have to do, don't put the reflective glass. Okay, no reflective flame. Okay, don't put the reflective glass. So instead you put a low emissivity film on the inner surface. Okay, so because of that, what happens? A large fraction of the sun's rays it is transmitted into the room. Okay, a large fraction of it, sun's rays is transmitted into the room, and since you have put a low emissivity film on in this inner surface, so I told you so that now the direct radiation is entering into the room. When it is entering inside, it will undergo multiple reflection. Okay, when it is undergoing multiple reflection, when it is coming and falling in this surface, because of low emissivity, it cannot okay go outside. It cannot go outside. Okay, so again it is reflected back. So it will be producing a greenhouse effect. Okay, into the room, it will be producing a greenhouse effect. So what will happen? The temperature of the room will be increasing. Okay, and that is what is required for us. Okay, that is what is required for us. We have to in colder climates. Okay, so we have to tap the solar energy. So for that we are creating a greenhouse. So by taking a glass with a higher transmissivity and with a low E film inside, low emissivity film being pasted at the inner side. Okay, and this is what it is done. Okay, and if you are just putting this technology here and this technology here, and it is going to be horrible for you, because if you are going to put a reflective film in a cold climate, so that means solar radiation will not coming into it. So that means inside you will be still it will be cold. Nighttime cold will be persisting inside in room. Okay, and similarly, if you are putting this okay without a reflective film, if you are putting this here in warmer climates, what will happen? Always the solar radiation will be entering into the building. Already it will be hot inside. Still it will be hot. Okay, so that this means you should be very careful. Technology what you are following, it should be very careful. Okay. Okay, so that is what I told. When you are in a cold climate, just now we had a detailed discussion. So you have to tap the solar energy. You should have a low emissivity windows. Okay, in the low emissivity film on the inner surface. Okay, so you have to reduce the conductive losses. Okay, during night time. I told conductive losses during night time. Underline this. Okay. During night time also you have to take care. So that means you can use multiple pan windows for that. Okay. So we are going to discuss about multiple pan windows, the technology of multiple pan windows. So that also it will be good. Okay. So you can night times you don't want to lose the heat from the building. Okay. So what you have to do? You have to increase the you have to decrease the U value. Okay. So that means how you can decrease the, you have to have an insulating glass. So the multiple pan windows are like insulating glass only. We are going to see that. Okay. So that means you should not lose energy in colder climate. You should not be a loser of energy in the colder climate. Okay. Similarly, you should not be a gainer of energy in a warm climate. Okay. So that is what you have to do. So here also the same thing, it is repeated here. So you have to put a heat absorbing film outside and a low E film inside. Okay. So that is, I think it is repeated. You can go through. Okay. So U value. I told during a night window, I think winter night, this U value is very important. Okay. So that means U value, it is not about solar heat loss or solar heat gain. Okay. That means the solar is not at all involved. Okay. It is just a temperature. That means it is very much relevant only during the winter night times. Okay. Coldest winter night times or cold winter night times, this U value is very relevant. Okay. So how to calculate the U value for the window? Okay, so if you are having maybe you will be having frame and you will be having the edge of the glass, you will be having the center of the glass. How you are going to calculate that overall heat transfer coefficient? Okay, so the formula is available. Okay, so this is available. Okay, so the total heat transferred is the heat transferred by the center, edge, and frame. So that is this is center, this is edge, and frame. So how you are taking? I'm taking overall for window. I'm taking what is U value. How I am calculating the U value for overall window? I am doing it by area weighted average. Okay. First I am calculating U for the frame. Similarly, I am calculating U for the edge. Similarly, I am calculating U for the center. I'm calculating U for center. I'm calculating U for the edge. I'm calculating U for the frame. Okay. Then I am multiplying by corresponding area. So and dividing by total area of the window. So because of that, I am getting what is overall overall heat transfer coefficient for the window. That is what I am using it here. Okay, so that is how I am to use it. Okay. So this calculation becomes very important for cold countries. Okay, and similarly, whenever the glass is there, how to calculate the resistance? How to calculate the resistance? Why I have to calculate resistance? Because U I have to calculate. How to calculate U? So it is outside resistance, thermal resistance outside, that is convection resistance. I'm sorry, convection resistance outside. Okay, similarly convection resistance inside, and L by conductive resistance of the glass, that is L by K of the glass. Okay, so if I add these three things, I'll be getting the resistance, total resistance. I take reciprocal of that 1 by R total, it will give me the overall heat transfer coefficient for the glass. So that is how I can find out how much heat is lost from a building or gained from a building using that U value by conduction. Okay. So I was just telling about insulating glass. Okay, insulating glass units. So this is one such insulating glass units. So here this is called a planned glass. Okay, a panned glass can be a single panned or double panned glass. So here double panned glass is shown. What is panned glass? So you will be having one glass here, and one more glass also will be here. So in between you can fill up with air. You know already air is air will be having lower thermal conductivity. So that means it will be acting like an insulator. So when I have this one system alone, okay, one glass, that means two glass with intermediate air. So that is called single panned glass. Okay. So here what is shown is the double panned system. So that means one air gap is there, one more air gap is there. That means a double panned glass. Okay. So this is the glass will be looking like this. Okay. So the glass will be looking like this. So you have to just take it and put it in your window. So that is it. Okay. Mostly it will be useful for winter countries. Just now I told you, no, it will reduce the overall heat transfer coefficient, which is very important for winter countries. Okay. And yeah, so how double panned glass it will be working? Okay. So double panned glass. You can use it for even summer condition also, okay, in our place also. But first and foremost, you have to paste the reflective film. Okay, so then only it will be effective. Otherwise, it will not be effective. Okay, So here it is shown. Okay, first I am putting a reflective plan. So then I am having a double glass. I mean a double glass with the airspace in between. Okay, so in a double blind glass. Okay, so this property U is calculated by 1 by HI plus 1 by HO, because we are having air fluid inside. Now I cannot calculate L by Ka, so I have to calculate again convection coefficient only. So the convection coefficient is 1 divided by H space, that is the resistance. H space. For air, you know, the convection coefficient in a closed space, air is filled and closed here, sealed here. So the convection coefficient will be lesser only. Okay. So but that means out of this resistance, so this resistance will be very much lesser. So that will help you. So that will help you in decreasing the heat transfer coefficient, or decreasing the heat which will be entering into the building by conduction. Okay. Okay, so this is double band glass, and this double band glass, if you remove this sun, you can use it in winter also, winter location, where you can even remove the reflective film also. So night time it will be working as a perfect insulator. Okay, yeah. And if it is a double planed glass, we will do one more thing also. So in a double planed glass, I'll be having two glass here. Inside the surface, I will be fixing with low emissivity films. Okay, very important. So inner surface, I am putting low emissivity glass. Okay. Similarly, this is a single band glass. Okay, and you can fill it with air, argon, or krypton. So just now we have seen only air. You can even fill with argon, and even you can fill with krypton. Okay, with our inert gases. Okay, so this filling of inert gases causes to reduce the overall transfer coefficient. That is, overall heat transfer coefficient will be drastically reduced if you are going for argon and krypton. So that is what we are finding here. And what is the emissivity of the film which you are pasting inside? So that is given here. So that is we are coating with a 0.1. Okay, on surface 2 and 3. This is 1. This is 2 and 3, and this is 4. So on inside surface we are coating with the low emissivity films. Okay. Similarly, I have a triple pan window. So a triple pan window. So here you can see three glasses are there. 1, 2, 3. Okay. So this is a triple pan glazing. So inside we will be filling with inert gas, and here you can see in 2, 3, 4, 5. I am fitting with the low emissivity glass. Okay. So you can ask why I have to fit this low emissivity glass here. Okay. Heat will enter here. Okay, from this point to this point, heat can if I'm putting a krypton gas, so heat cannot enter by conduction or convection. Okay, so heat can enter only by radiation, but I am putting a low emissivity on both the sides. So that means less heat only will be emitted from here, and less heat only will be absorbed from here. So this is the basic principle which is applied in a thermoflux. Okay, so yeah, there also we separate the two surfaces, and we are putting low emissivity surfaces. That means it will be reflective. Okay, so because of that, heat will not be transferred. Okay, radiation heat will not be transferred from this surface to this surface. The same concept we are applying here. 2 and 3 also we are putting low emissivity. 4 and 5 also we are putting low emissivity, and we are filling with the krypton gas. So what is happening? Overall heat transfer coefficient, it is reduced drastically. So here you can see overall heat transfer coefficient. So this type of glass, it can be called as a perfect insulator, which will be very much suitable for winter locations. Okay, when you want to use it in summer location, first put your reflective film on the first side, then you can use it. Okay. Okay, so that is how you will have a double pan. Okay, so double pan glass. Okay, so it is like insulating glass. Inside you can fill it with whatever air, argon, or krypton gas. Okay, so for and the inert gas you are filling it inside. Okay, so there will be convection circulations inside. Okay, but it will be acting as the insulator. Okay, so we have a triple band glass, and here how much you are having? So 1, 2, 3, 4, 5 band glass you are having. So now you can see it is commercially available. It is like just pulling it and putting it in the slot. Okay, these glasses it is available. You have to just put the glasses in the slot, and you have to. So that is commercially available. Okay. Okay, so and you can calculate the heat transfer coefficient for airspace. Okay, and similarly you can so you can find out. Okay, so these tables I think you can go through. I don't want to take more time because Sunday then you will be you may not like that. Okay, so okay, now what is the U value? Okay, so what is the U value for single glazing, double glazing, okay, and triple glazing, and so what is that you are finding? So that the U value, so if because of this thickness and double glazing, you are finding it is decreasing. So here for a clear glass it is 6.3, for argon, okay, 12.7, double glazing it is 2.61, triple glazing it is 1.65. Okay, so with the argon space at 12.7 thickness, the thickness is increased, again it is decreasing 0.8. So that is what if I do all these things. Okay, so my um, insulation. Okay, so insulation will be good. Okay, insulation of through using glass. Okay, so that will be good during winter seasons. Okay, and when you are using glass at the skylight area, so that means at the top roof and all. So the amount of radiation transferred. Okay, so that will be very much higher. Okay, so that we have to take. Okay, that is point number one. And if you are using multiple glazed unit, okay, so you can for increasing the performance, you can fill up with the CO2. Just now we have seen air, we have seen, then we have given neon and krypton also we have seen. So like with carbon dioxide, you can fill it. Okay, so you have to fill a gas with low thermal conductivity. Okay, so you can use krypton gas also. Okay, and coating of low emissivity films. So that also you have seen, which will be reducing the okay, so U factor significantly. And this and all we have seen now. Multiple glaze units also we have seen, and increasing the thickness of the multiple glazing unit, and increasing the air gap or the gas gap, the krypton gas gap, that also will be increasing the decreasing the U value. That is what we have seen. Wood and vinyl frames are the best material for taking the metal frames for the windows. Okay. Okay, so now we will try to consolidate what are all the things we have studied: the insulated, double glazed, triple glazed. So that is now we have studied. Okay, double. So this is all insulated glasses, double glazed and triple glazed. Just now we have studied. Gas filled glazing also we have studied. So that also it will be increasing the performance. So gas filled it will bring down the thermal conductivity 1 to 0.2 to 0.3. So this is commercial. It will be a little bit exaggerated. Okay. Similarly, there are some special type of glasses called spectrally selective glass. So spectrally selective means when solar radiation is falling on your house, so you can use a glass which will avoid all the harmful radiations. Okay, so that you can do it. Similarly, if you want to avoid the short radiations also, that also you can do it. So a multiple layer of silver, if it is coated, okay, it will allow only glass to selectively to transmit. Okay, and it will reject the certain wavelength. So it will be like a sunglass, Ray-Ban glass and all we are wearing now. Some light will be very pleasing for the eyes. Okay, so likewise in glass also you can be spectrally selective. Okay, and you can use it. So this is possible. Okay, and reflective coatings. So this is very much it is known for everyone, because in our India also most of the buildings are like this only. So here we have metallic layers. Okay, we coat the metallic layers like silver, gold, and bronze. Okay, so these metallic layers are reflective coatings are applied on the surface of the glazings. Okay, so because of it will improve the reflectivity. Okay, and it will reduce the transmissivity. This will be increasing the visible light transmittance. So that also it is very important parameter. Okay, for the glass. Low emissivity coating, so that we have discussed now. So how we do the low emissivity coating? So microscopically thin, virtually invisible metallic or metallic oxide layers are deposited on the one side of the window. Okay, so that is how we do that. But where we are going to put our low emissivity, that is very important. Okay, in a winter country you are going to put it inside. Even in the summer country also you are going to put it inside only. Okay. And heat absorbing tints also we have discussed so far. So we have a gray and brown bronze heat absorbing tints. It is cheaper. Okay, it is cheaper, and SC value and SHGC value will be lesser. Okay, so this is also before the advent of this heat absorbing films and heat reflecting films. Okay, so these were used in India. Okay. Okay, so now we will end up with our discussion with a special type of glass. Okay, it's called a smart glass. Okay, so what is a smart glass? The smart glass is a material, optical material, that is a glass material used for windows. Okay, where you can alter the optical and thermal properties. Optical means what? Transmissivity only. Transmissivity and reflectivity, so that you can alter, so that it will be so this glass will be like optical and thermal modulation will be done by this glass. Okay, so that you can, this principle you can use it for controlling the flow of light and heat into the window. Okay, so it is like a sunglass. Okay, so I think whenever sun is there, your specs will go into dark. Okay, so that is how. Okay, so that is the concept. And how this is happening? So a large change in the optical properties or a change in the light intensity. So if there is a change in the light intensity, glass will change its optical property. Okay, similarly for this for the spectral composition also it will change. That is what we said, a selective absorption. Selective absorption of similarly, based on heat also it can change in optical properties. Similarly, based on electric field also it can change the optical properties, or injected chemical charge also it can do that. Okay, so we are if you are using a combination of all these external excitations for changing the glass property. Okay, so that is called as a smart glass. Okay, the optical change will be resulting in the from a highly transmitted state to a partly reflecting or absorbing state. So it means from a highly reflecting, okay, so highly reflecting means it will be like a, first the glass will be like a totally transmitting glass. Okay, so after that, after application of this thing, your smart glass will become partially reflecting or absorbing. So you can set, similarly, like you can set how much amount of light should enter inside or how much it should leave outside, so that you can set it. Okay, so you have the electrochromatic window which change the light transmit and transmitting shading of the windows in response to environmental signal. So what are all the environmental signal? It can be light intensity, spectral composition, heat, electric field, or electric charge, injected charge. So how this is working? Okay, so I have three layers. Okay, so one is active chromic electrochromic layer. So this is the active electrochromic layer, and I have a passive counter electrode on the other side. So in between, I'm having the electrolyte. Okay, so when I'm giving the voltage, I'm giving a voltage to this system. So when I'm giving the voltage in this direction, now what it is doing, it is taking both the light as well as heat. That means short radiation as well as long radiation it is taking inside. So now what I'm doing, I'm just reversing the voltage. Here you can see I'm reversing the voltage. Okay. So when a reverse voltage is applied, okay, so what is happening? Here you can see, so for the active electrochromic layer, so there the molecules are not arranged in the first stage. But I reverse the voltage, now you can see these molecules are arranged. Okay, now these molecules are arranged in this state, it is blocking the short radiation. So that means it is reflecting the heat and just allowing the light alone. Okay, so that is what is required for us. So that is what we call the smart glass. And if it is happening in step, that will be still better for us. That means for a low voltage, it will allow less light. I'm increasing more voltage. Okay, so that means it will allow more light. Okay, so if it is happening like that, okay, so then it is very good for us. Okay, so how this arrangement is there? Okay, so the arrangement is like you have the glass plastic sometimes outside, then I have transparent conducting oxides inside, and then after that I have electrochromic ion conducting electrolyte just now you have seen, and ion storage here. Okay, so what is that we are doing? We are applying a voltage across the transparent conducting layer. So these two layers I am applying. Okay, so what is happening is this will cause the hydrogen and the lithium anions. Okay, so hydrogen and the lithium anions to move towards the electrochromic layer. It will move towards the electrochromic layers, and because of that, it will go for blocking the sunlight. Just now we have seen the molecules are not arranged properly. Then it will get aligned. So then it will try to allow the light. It will try to block the light. Okay, and if it is happening in the steps, then it is good for us. So you can see here, depending on the voltage, so the transmission of light, it is varying. Okay, so low voltage, then I'm increasing the voltage in millivolts. So you are finding this transmissivity is increasing. Okay, so that is what is required for us. So that means if you are able to allow the light into the building in steps, okay, then it is good for us. So what you have to do, just to change the voltage. Okay, by changing the voltage, you can change uh, the light allowed into the building in steps. Now this thing is happening in the apps, mobile apps itself. They are doing. Okay, so you can see in the YouTube. Okay, so they are doing it in the mobile apps itself. Okay, they are controlling the light in entering into the building with the mobile apps. So that is possible. Okay, so okay, I think we are here. Okay, yeah. So this is how when I give a voltage, how the color of the glass changes. Okay, so that is what is given here. And if a room is like this, okay, so after applying this step voltage, okay, so here you can see the same time, now you are changing the transmissivity of the glass. Okay, now you are doing electrically. So because of that, what is happening, before the room was like this, now you are able to make the room like this darker. Okay, so that is good for you, no? So that is what we call it as the smart gas. So that means now this is applied. So they call it as a sensitive envelope. Okay, sensitive envelope, and in response to the light, these things will be changing. Okay, so this is latest technology. Thank you for your passionate. So any question is there, I can answer. So any question is there, you can put it in the chat box. Okay. So no question is there. What is the optimum value for VLT? So it depends on how much light you require. Okay. Yeah. So it depends on the space. Okay, it depends on the space. So you are the designer. You have to design how much visual light transmission is required. Okay. Yeah. And this how much lighting is required, it depends on different design conditions. For example, if you are taking specific industries, okay, so lighting required will be different. Okay, so, and some other theater and other things, so the lighting required may be less. Reading room, the lighting required will be more. So in that only, okay, so like that only we can understand. Okay, so it all depends on you. You are the designer, so based on that requirement, you can select the class. Okay. Yeah. So any other question is there?
Sir, I have one question.
Yeah.
Sir, we discussed about June solstice. So we got to know that maximum heat load will occur in the month of June because of June solstice in locations such as Bangalore and Chennai. So it is necessary that the maximum heat load will occur in June only, or it can occur in April or March month also.
No, yesterday itself this question was there. So I'll tell you very clearly. Okay. So the thing is very simple for you to do that. Okay. First thing is for Bangalore. Okay. What is the latitude? Let us finish this today. Okay. What is the latitude? Can you go? Can you Google and tell me?
13-degree north latitude.
13-degree north latitude means so it will be May. Okay. So May, the sun will be peak. Okay, sun will be peak over Bangalore in the month of May. Okay, so that is point number one. And the sun will be moving towards the north. Okay, sun will be moving towards the north, and again it will be returning back. Okay, so maybe in July, August again it will be returning back to the overhead to the uh, Bangalore. Okay, but 2 points. So whenever the first time the solar radiation is falling on Bangalore, so at that point of time, uh, the heating of Earth will not be there because it is a Bangalore is going from a cold zone from December to March. Okay, March April, it is going through a cold phase. Okay, and that is the first time. That is in the month of uh, May. So it is first time it is coming overhead sun. Okay, but what is happening after that? So there will be a daily variation. If you see, there will be the rise in daily ambient temperature. Okay, so this daily ambient temperature, it will have like a storage effect. Okay, I don't know whether it will be available in Bangalore, but in Chennai, that effect we can know very well. Compared to April, May, so June, July, it will be very hot. It will be unbearable. Okay, so the reason is daily it will be heating. Okay, so that means that heat will get accumulated. Okay, so that you can understand if you are going for annual simulation. Annual simulation means year-round simulation. So in year-round simulation, I think I have shown you also the cooling load will be increasing gradually. So up to August, okay, I mean May, okay, it will be increasing. After that, it will not be decreasing. Still, it will be increasing. It is because of that heat transfer effect. Every day, some amount of heat will be added to the ground. So in winter, it will be taken back. So that's why the temperature will drop. But here, still you are adding incrementally. If you are adding heat, so what will happen? The temperature will still increase. So that because of that effect, you will be having a higher temperature. But Bangalore, this effect, whether it will be available, I don't know why, because Bangalore it is at a higher altitude, so it will lose heat. How it is gaining heat, the same way it will lose heat also. Okay, but this effect you can see in Chennai. Okay, if you are Chennai, you can know very well. Okay, so this heating effect you can. So even in Bombay also the same thing is possible. Okay, this accumulation of heat from the month of May till June solstice. Okay, so that will be happening. Okay, it will be increasing. The rise in temperature will be happening. So that is why I suggest to take June solstice. Okay, most of them they are taking June solstice. But in data book they will be telling that the sun is overhead on the month of April for Chennai or for May for Bangalore. Okay, so you take that one also. You take that one also. But realistically speaking, with the climate data, if you find it, so whatever I am saying, that is going to be there. Okay. Yeah. Have I answered, Brijesh?
Yes, sir. Thank you.
Yeah. So the best thing is you do the annual simulation. Okay. So if you do the annual simulation, you can see that the trend. Wherever it is maximum, you take it as the load. That is the best thing. Okay. Okay. What type of glass used in the residential building other than cold climate? Okay, so other than cold climate, so you can have tinted glass. You can have glasses with tinted glass. You can use it. It is cheaper, and you can go for films. Okay, films that is dark films. Also, you can go heat reflective films. Also, you can go in warmer climates. Okay, so on the outer side, and the thing is you can go the best if you have more money. You can go for double band glass or triple band glass also. On the front side you can paste it with the reflective glass. Okay, I mean reflective film, I'm sorry. On the front side you can coat it with the reflective film, and you can on the this will have insulation effect as well as it will avoid the radiation entering into the building. Okay, warm and humid climate. Okay, so warm and humid climate, so just now what I told. Okay, so you want a cheaper glass, go for tinted glass. Okay, tinted glass. If you want to go for films, you can go for darker shade films. Heat reflective films will be better than that. Okay, so it will reflect the heat from the surface. And if you have more money, you can go for double band, triple band glass with reflective films. Okay, yeah. For simulation, SHGC or SE is important. For simulation, we may not go for SHGC or SE because whatever the analysis I told, we will be taking transmissivity, all the properties we will be taking. When you are taking the material, we will be taking the property and we will work out, because in SHGC we are not splitting the transmissivity into direct component and diffuse component. But in simulation we will be splitting that and we will be taking the exact value. Okay, in heat load calculation only we will be using SHGC. Okay, so that is an approximate thing. So approximate calculation we are doing. If you are going for simulation, so mostly in simulation you go for accurate prediction. So that means you will split the transmitted radiation into direct component and diffuse component. So for that, you will be giving the corresponding properties, and you will be trying to find the exact value of radiation entering into the building. Similarly, even absorbed value also you will be splitting into two, as the direct component and the diffuse component, and then you will be working out. Okay, so SHGC is an approximate method. Okay, it is not even splitting that into direct and diffuse component. Okay, and even area also, it is just giving one area only, full area only. But in reality, okay, so you have the area for direct component is different, area for diffuse component is different. Okay. Okay, so any other question is there? So cost, I think you should ask with the engineers who are working in the field. Okay. Yeah. Should not ask a professor. Okay. I think most of you will be knowing. Okay. Most of the engineers, they will be knowing about the cost. Okay. So yeah. I'm sorry. So any other question is there? Okay. So if there is no question, thank you for joining today. Okay, so in spite of being a holiday, for a special session, most of you have joined. Thank you for joining. Thank you very much.